Okay, last lesson, polar equations and the calculus of polar equations. We'll start with derivatives, first semester stuff with polars. Well, if I took the derivative of this guy, and I would just get r prime is equal to negative 4 sine theta, what does that give me? Well, it actually gives me dr d theta. I'd be taking the derivative with respect to theta of this equation, and r prime is really dr d theta. What is dr d theta? It's the change in the rate of the radius with respect to the change in the rate of the angle. What is that? Well, I don't know. It depends if you're looking for something. It's not something maybe we can understand visually in terms of like a tangent slope, because we know tangent slopes are dy over dx. This is the change in the radius over the angle. However, if I say set r prime equal to 0, that'll help me find a max or a min r. But it's a little bit more complicated than that. Like if I asked you what the max distance from the origin, or the max or the min distance from the origin for r equals 4 cos theta, what would I do? Well, I would take negative 4 sine theta, set it equal to 0, and what do I get, Mr. Siddiqui? You're using your phone, I'm calling on you every time, okay? I'm just going to say that right now. No, just what do I get? What do I get?
You get negative 1/4.
No. When is sine of theta equal to 0?
At 0.
Good.
And pi.
Good. Okay, so that's going to be locations of max or min r's. Well, that makes it a little bit complicated, though. And if I looked and I could do this, 0 pi, I could do 2 pi if I wanted to. I would see that's when we're between 0 and pi, sine is positive. Between pi and negative 2 pi, sine is negative, and then it will be positive. So that means pi most likely is going to be a max.
But does the negative 4 change?
Oh, jeez, yeah, sorry. Flip-flop those. Minus, positive, minus. So, sorry, and it'd be plus between that. It looks like 0 would be a max and pi would be a min. Well, it would be a max r and a min r. However, distance makes it a little bit complicated. Let's look at the graph of 4 cos theta in our calculators. Here's the graph of 4 cos theta. What is the maximum distance that r can be? They're all the same. From the origin is what I'm talking about, not from our center. 4, right? 4 is the max distance. What's the min distance? 0. Well, we said that 0 is our max and pi is our min. Well, turns out when I graph this, and let's go ahead and go around, sometimes it helps if I grab this, and that way I can look at it really quickly. Copy, paste, shrink. Oops. If I go around the circle with my angle, so that I can plot points, here's 0. The min distance appears to be 0, but where location is that? Grab it. There it is. That actually is at pi over 2. When r is 0, that's pi over 2. Turns out, when I start going over here to 3 pi over 2, 5 pi over 6, and pi, I'm graphing these points with negative radiuses. So actually, pi is a min, but it's a min because the radius is negative. So all of a sudden, this distance question is, wrong. This would be the wrong answer to this. If we want to find the max r and the min r, we could say it's at locations of 0 and then pi. That's a max because r is equal to 4 there. This at pi, we got to remember that radiuses can be negative. If I'm over here at the angle pi, cosine of pi is negative 4. Negative 1 times 4, negative 4. Okay? So an example of that, maybe you ask a question, what is the max r for a certain polar equation? That's question number 1. Maybe you have a question where you have r is equal to, I don't know, we'll stick with 4 cos theta. Some questions will be with respect to time, so related rates problems, only find dr dt when theta equals pi over 6 and r is equal to, and d theta dt is equal to 2. Well, I can do that by taking the derivative with respect to t of r equals 4 cos theta. Okay, so this is like a related rates problems with polar. I would get dr dt is equal to negative 4 sine theta d theta dt. I'd plug in theta, which is pi over 6. Sine of pi over 6 is 1/2. So this would be negative 4 times 1/2. D theta dt is 2. So this would be negative 4. That would be dr dt. So we're changing our radius at this angle at this amount of time per second or minute or whatever t is in. Okay? I just made it up. Okay? It'll be something either given to you or usually it'll be something given to you. Now, tangent slopes of polar equations, we know tangent slopes are dy dx, right? Well, I don't have y's and x's if I have an equation with r's and thetas, but I can have y's and x's. How do I turn polar equations with r's and thetas into y's and x's? Yeah? Yeah, with our favorite friends, Mr. Sokotoa, Mr. Pythagoras, we know y is equal to r sine theta. X is equal to r cosine theta. Right? Well, what I'm going to be able to do is find y, find x, then take the derivative of y with respect to theta and divide that by the derivative of x with respect to theta. Because when I do that, all of a sudden the d thetas will go away. Times d theta, bye. We just get dy over dx, okay? So the process to find a tangent slope for a polar equation, figure out what y is. So let's do this example. Figure out what y is. Y would be equal to r sine theta. Figure out what x is. X is equal to r cos theta. Then take the derivative of both of these with respect to theta, divide the two, and you have dy over dx, which will give you a tangent slope, right? Change in y's over changes in x's is slope. Dy over dx is instantaneous change in y over instantaneous change in x, slope of a tangent. Okay, so let's do that for this one. Now, we would find out that the derivatives typically use the product rule and are typically a little bit messy, but just keep things in order, you'll be okay. So derivative of the first is negative 4 sine theta times the second, sine theta, plus the derivative of the second, cos theta, times the first, 4 cos theta, divided by the derivative of x with respect to theta, which will be dx d theta. For cos theta is negative 4 sine theta times cos theta. Derivative of cos theta is negative sine theta times 4 cos theta. Right? Messy. But that's the derivative. Okay, maybe you ask a question where what is the formula for the slope of the tangent for this? But typically that's a little bit crazy. Instead say, what is the slope of the tangent at a specific angle? Now we're going to have to plug in pi over 4 everywhere. Sine of pi over 4 and cosine of pi over 4 thankfully are the same value, so it won't be that difficult. We'll have negative 4 times root 2 over 2 times root 2 over 2 plus root 2 over 2 times 4 root 2 over 2 divided by negative 4 root 2 over 2 root 2 over 2 plus negative root 2 over 2 times 4 root 2 over 2. Everything in the top ends up canceling, just giving you 0. Root 2 over 2 times root 2 over 2 is 2 over 4, so that's 1/2, times negative 4 is negative 2, plus negative 2 ends up being negative 4. So I have 0 over negative 4. So the change in my y with respect to theta is 0. The change in my x with respect to theta is negative 4, which is pretty much telling you I'm moving kind of to the left, but I'm not moving up or down at the location when theta is equal to pi over 4. Okay, so not moving up or down, but moving to the left. Let's go ahead and graph 4 cos theta. You already have that. And see how the graph appears when you start going over it. So 4 cos theta, I'm going to make sure I'm between 0 and 2 pi. I'll shrink my step a little bit so that we can slowly see it. I start at 0. There, my tangent slope appears to be 0 at pi over 4. Notice I'm going to the left at that situation, right? I'm going to the left there. So that's why this is negative 4. Now you can confirm that using your calculator. Your calculator can find a couple of things on the graph of a polar equation. Go to second calculate in your calculator. Yes, you'd put your answer as just 0. The slope of the tangent is 0. However, within that answer gives you a couple of interesting things. Okay, so you could calculate a value. So if you press value, it's just like trace. You would plug in a theta measurement, and you would find the x and y coordinates. I believe value might give you the r. No, they give you the x's and the y's. If you go to table, it finds you your r. You can also find dr d theta, which is just r prime. But here you have dy dx. dy dx at pi over 4. Go ahead and plug in pi over 4 to go to the specific angle. Then press enter, and you should see that tangent slope of 0. Now, again, your calculator uses 2 points really, really close together. This is negative 8 times 10 to the negative 8th. That is 7 zeros followed by negative 8. Some calculators might say 0. My calculator here says something essentially 0. So this is good. Okay, so something like that. Let's do another one, a more difficult one. Find the slope of the tangent to 1 plus 2 sine theta when theta is equal to pi over 3. How do we find dy dx? Step 1, what do we do? Yes, we need dy d theta and dx d theta. Before we get dy d theta and dx d theta, what will we need? X and y. Good. Make sure you remember y is equal to r sine theta. So I have y is equal to 1 plus 2 sine theta times sine theta. X is equal to r cos theta. So x is equal to 1 plus 2 sine theta cos theta. Now I'll take the derivative of the y with respect to theta, divide by the derivative of x with respect to theta. And then we'll plug in pi over 3 everywhere. Here we go. Derivative of this product, use the product rule. I have 2 cos theta times sine theta plus cos theta times 1 plus 2 sine theta. That's the derivative of the top, the bottom. Derivative of the first, again, 2 cos theta here times cos theta plus the derivative of cos theta negative sine theta times 1 plus 2 sine theta. Some teachers have you memorize like a formula for the derivative of a polar. I find that it's just much easier just to figure out what y is, figure out what x is, and go from there. Okay, again, messy. Plug in pi over 3. Let's see what we get. Cosine of pi over 3 is 1/2. Sine of pi over 3 is root 3 over 2. So I have 2 times 1/2 times root 3 over 2 plus 1/2 times 1 plus 2 root 3 over 2 divided by 2 times 1/2 times 1/2 plus negative root 3 over 2 times 1 plus 2 root 3 over 2. Let's just go ahead and try to simplify this so that the calculation can be easily done. This would be root 3 over 2 plus 1/2 plus root 3 over 2, which gives me 2 root 3s over 2 plus 1. In the denominator, I'd have 1/2 plus negative root 3 over 2 plus, this would be, the 2's would cancel, negative 3/2. So this would be negative 2 minus root 3 over 2. I can simplify these two fractions. The 2's would end up canceling when I multiply by the reciprocal. I'd get 2 root 3 plus 1 over negative 2 minus root 3. Confirm that that's correct. Go ahead and graph 1 plus 2 sine theta. What does that even look like? Look at that. It's even cooler than an oval. It's got a little inside part to it. Now, it's very important to understand how this graph is created. Where do we start? Do you think we start at 0 and we kind of come around here? We start at 1, exactly. When the angle is 0, let's go ahead and grab this as well. Very, very important, especially when we get to the next part, when we start graphing things, to understand how this graph is plotted. Get your angle, you start at 0. So it appears that we start at this point 0 when the 1 comma 0. So the radius is 1 when the angle is 0. Now, let's remember we have r is equal to 1 plus 2 sine theta. That makes sense. Sine of 0, 0. I have a radius of 1. Here's my first point. Now watch what happens. As I go around, there we go. This is pi over 6, pi over 4, pi over 3, pi over 2. I'm still on this outside part here. Okay, so I start here, and I go up here. Then I would continue to follow it, still positive values, and then when I get to pi, I go here. So this point right here would be the point negative 1 pi. This is the point 1, 0. Right? That's kind of confusing because watch what happens. I'm at pi, but I don't have all of my graph. When I go to angles beyond pi, what is going on with my radiuses? This is between pi and 2 pi. What are the radiuses? They end up starting to become negative once I get to a specific angle. It looks like right here. Once I get here, the radius becomes negative. Okay? So watch here. When I'm at 3 pi over 2, I have a radius of negative 1. This point right here is negative 1, 3 pi over 2. That's how you graph that. So there are some questions, and we could talk about it later. It's like, what is the area of the inside piece of this? You'd have to figure out what angle it starts at. So whenever this is equal to 0, you would be able to solve that. And then you'd have to start there, and you'd have to end at the other angle when it also equals 0. So just understanding how things are graphed and where these points come from, very, very important. But go back to the problem. We're just going to confirm that the slope of the tangent at pi over 3 is this value. If I look at the graph, again, at pi over 3, it looks like it's a negative tangent slope, right? Go ahead and in your calculator, calculate dy dx. And then in my calculator, I will calculate that fraction. And let's confirm that our answers are going to be the same, okay? Okay. So 2 root 3 plus 1 over negative 2 minus root 3, comma, 2 root 3 plus 1 divided by negative 2 minus root 3. Did you get this in your calculator? Negative 1.196? Good. All right. So just like I suspected at pi over 3, my tangent slope is negative. You could find that in your calculator by graphing and doing second calc dy dx. There's probably a question where you're finding dy dx of a polar equation at a certain point. Okay. Horizontal and vertical tangents. Remember, horizontal tangents is when what happens?
Numerator is equal to 0.
Yeah, when your tangent's horizontal, that's when you have a horizontal tangent. It's when your slope is 0, right? Or, in particular, when your numerator is equal to 0. Well, if I have a vertical tangent, that's when dy dx is what? Undefined. Or when your denominator is equal to 0. Well, in polar equations, dy dx is dy d theta over dx d theta. What do we have to find? Just when dy d theta is equal to 0. Here, we would just have to find when dx d theta is equal to 0. If you were asked a horizontal tangent or vertical tangent question, you don't have to find dy dx. Instead, you just need the top half or the bottom half. Okay, now let's do a question. When does 5 sine 3 theta have vertical tangents? Vertical tangent occurs when what? when dx d theta equals 0. How do I find dx d theta for r equals 5 sine 3 theta? I can't just take the derivative because that'd be dr d theta. Good. We need x first to have dx d theta. X is equal to r cos theta. Don't forget that. X is equal to 5 sine 3 theta times cos theta. And I'm going to change the question. We're going to find its first vertical tangent when theta is greater than 0. Okay, so I just want one vertical tangent. We'll find there are multiple. Okay, well, I need to find dx d theta and set it equal to 0. Let's go ahead and do that. The derivative of the first, 5 cos 3 theta, chain rule, multiplied by the 3, times the second, plus the derivative of the second, times the first. Set that equal to 0. Now, I told you that you can use a calculator. And that's a good thing, because trying to solve this is going to be difficult by hand. How would we solve that using a calculator? Yes, we would graph these. Now, let's go ahead and attempt to graph r equals that and r equals that. Well, before you go ahead and do that, let's just do a little test. Let's say I have 4 cos theta and 4 sine theta. What am I attempting to do when I'm graphing both of them? What am I trying to find to solve the equation? Good. So we have to find the intersection. Let's say I have an equation 4 sine theta is equal to 4 cos theta, and I want to find these intersections. Well, I would typically go to second calc, and what would I look for? Intersect, right? Do I see intersect anywhere? No. So in polar mode, you can't do this. But guess what? This is just an equation. You can still use y equals, and then instead of thetas, x's. You'll just get answers with x's, but they will correspond to theta measurements. So to solve this equation, let's turn our calculators back into function mode, and let's graph this. Let's find the first intersection, and let's confirm that that's going to be the location of a vertical tangent for 5 sine 3 theta. Why am I freezing? I guess I should freeze so that you can see it. Is everybody doing it? It's probably taking a while to graph. You might want to shrink your window to be from 0 to 2. The first one when theta is greater than 0. So I don't have to look at any of the negative values. Here's the graph of that between 0 and 2. Now, if you go back to Zoom Standard, actually, how many intersections do you see? Super lot, right? Probably there's an infinite amount of these vertical tangents. Does that make sense to have an infinite amount of vertical tangents? Let's look at the graph of this 5 sine 3 theta. 5 sine 3 theta, I already graphed it over meh. Okay, 3 petals, pretty cool, right? Well, it looks like I have how many locations of vertical tangents? 1, 2, 3, 4. How come my graph is telling me I have like 20 intersections, which would mean 20 vertical tangents? Exactly. As we continue to add to theta, we continue to retrace this. So as I continue to go around, we'd have an infinite amount of locations of vertical tangents, right? Because we just keep going around the same graph as theta gets larger and larger and larger and larger, okay? So that's why the question is find the first one. So the first one appears to be right here if I talk about starting at 0, 0 and moving around the circle. It looks like when I go to pi over 2, we'll be back at 0. No, less than that. So what would this angle be actually? Where we'd go back to 0? It'd be pi over 3, right? Because the sine of 3 times pi over 3 is the sine of pi, which is 0. Okay? So anyways, let's just find this first one. I go to second calc intersect. I've moved my window so that I can just see a couple. I go to this first one, which is over here. Enter, enter, enter. And you get 0.467964773. So x equals, which is the same as theta equaling 0.467964773. Confirm that's correct by graphing 5 sine 3 theta back in polar mode and then looking at the point when theta is equal to that. Yeah. Do it. Graph 5 sine 3 theta in polar mode. Go to the angle measurement of 0.467964773 and confirm that it's this location right here where we have a vertical tangent. Is it? Well, it's because we did everything right. Five sine 3 theta graph. Zoom. Standard. Notice it's going over the graph again. Makes it a little thicker because of the step. Anyway, zoom standard. There's my 1, 2, 3 petals. Here's it tracing over it again, showing you that you can have an infinite amount of locations. Second calc, or just go straight to trace and plug in 0.4796473. Is that it? Boom, vertical tangent. Great. Okay, so probably a vertical or a horizontal tangent question. Probably the question you have to solve using your calculator. Great. Moving into the second semester of calculus, so finding areas inside polar graphs. Let's recall areas under functions, y equals f of x functions. How did we find those areas? We used an integral. What did the integral stand for? An infinite sum. And what were we taking an infinite sum of? Yes, a y times a dx. And what is that? An area of what? A rectangle, right? We took an infinite sum of skinny rectangles. I hope we understand this, because this is crucial to the entire course of calculus. The skinny rectangles all had heights times widths. This is the height, this is the width. Well, the height came from a function value, which is a y value. The width was an instantaneous change in x, which is why we had f of x dx. It's multiplication. It's an infinite sum of things being multiplied, giving us skinny rectangles. Now, here's the issue, though. If I took a rectangle like this, it looks like I'd be over the actual area. Why am I comfortable with this being the actual area if I know sometimes rectangles are over and sometimes rectangles are under the actual? Almost. Looking for a better answer than that. No? Yes, Miss Arthaler. They're infinitely small, so what does that mean? It's just the point. Pretty much it's the point with so small of a width that you're just taking a line right underneath that point and you're adding up all of these lines to get your areas. It's not over or under anymore because things are infinitely small, right? Okay, well, that was first, the second semester of this course using functions. Well, now we can have a polar curve. This is a polar curve. The key is, and this is very, very important, we are not going to be finding the area under the polar curve. We're not talking about from here to here. Because if we did that, we'd have to use dx's, and we'd have to use y's, and we could actually do that as long as we change things into x's and y's. But no, that's not what we're finding. We're finding the area inside. Not difficult. Because instead of taking an infinite sum of skinny rectangles, we'll be taking an infinite sum from one angle measurement to another angle measurement of skinny pizza slices. What do I mean by pizza slice? I mean I'm going to take an angle measurement, come out here, and connect these 2 points with a circle, kind of an arc of the circle. And this would be a theta measurement here. And then I would do another one here and connect them with an arc of a circle. Okay? And I would take an infinite sum of very, very skinny pizza slices. Well, we found out the area of a rectangle easily, base times height. What's the area of a skinny pizza slice? Let's figure that out. We know what the area of a circle is, right? Good. Well, let's just take a section of the circle, or a pizza slice of the circle. There is a pizza slice. It is denoted by a theta measurement. Let's do that theta in a different color so I can fill this in. How do I find the area of that pizza slice? That's exactly right. If you think about if I had a quarter of the circle, I would take the area and divide it by 4, right? Or multiply by 1/4. Well, however much this angle is divided by the total distance around the circle, that would be the proportion of the total area that I would need. So I just need, I'll do area of a pizza slice, pi r squared times that theta measurement over what? Yeah, so 360 would be perfect if we were talking about degrees, but 2 pi because we're talking about radians. What happens? Well, look, the pi's cancel. Turns out you don't need pi. Well, sometimes you'll need pi depending on what theta is, but all of a sudden the area of a pizza slice is just going to be 1/2 r squared times the theta measurement. Right? This is key. Because what are we going to be doing? We are going to be taking an infinite sum of 1/2 r squared times theta. However, what is happening when I'm taking an infinite amount of pizza slices to theta? If I take an infinite amount of pizza slices, so if I take more and more pizza slices here, what's happening to this theta? What is theta becoming? Yes. How small? Infinitely small. What is the notation I can use for something infinitely small? D theta. Aha. We have a formula now for area inside of a polar curve. It's just 1/2 r squared d theta, which means you don't need to worry about theta. Just the integral will take care of the theta. Right, Mr. Emerson? Great. Now you can move the 1/2 in front, and it's 1/2 r squared d theta. We'll skip that. Come back to it if we need to. Certain issues with polar area. In your calculator, so many students do not put the entire r and square it. Make sure you have your 1/2 integral from a to b. You will have parentheses. Put your r in parentheses. Make sure you square the entire r. The main issue, though, with polar area is knowing when the graph stops or completes itself once. Because you do not want to double count areas. Here's a perfect example of that. Here is 2 sine theta. It's a circle of radius 1. Now, if I use the formula, 1/2 r squared d theta, well, it looks like we're going around the entire circle. I go from 0 to, looks like 2 pi. I'm going to put 2 pi here. Go ahead and type this into your calculator and figure out what that area is. So we're talking about the area of this entire circle. Going out like that. Okay? 1/2. Now you don't have to be in polar mode to find area. You could be in function mode. Doesn't matter. But go to your home screen. Math 9. 1/2 0, 2 pi, in parentheses, math 9, 0, 2 pi, in parentheses, 2 sine theta squared d theta. Make sure you have the correct set of parentheses. Something happened there.
And we'll play by a half at the end, but not to do it. I forgot. Got it? Oh.
Physics. What do you get? 6.28. What does that equal to? You didn't get 6.28. It's because you didn't put 2 sine of theta in parentheses and square it. If you got 3.14, you plugged it in wrong. Where's your calculator, Ms. Cohen? You should be practicing this. Is that correct? What's the area of a circle with a radius of 1? Pi. I said that the area was 2 pi. Well, this is definitely right. This can't be right. Why? Because we're going around the circle twice. Let's see. I start at the point 0, 0, when my angle is 0, my radius is 0. These would be the points at pi over 4, pi over 3, pi over 2. The sine of pi over 2 is 1 times 2 is 2. There we go, we're at the top. Here is 2 pi over 3, 3 pi over 4, 5 pi over 6. Pi gives me 0. I am around my full circle. I have plotted my full circle from 0 to pi. If I continue to go around, what is happening to my radiuses? Exactly. R is negative when theta is greater, or when theta is between 2 pi and pi. If you go from 0 to 2 pi, you will be finding the area of the circle twice, which you don't want. So change this from 0 to 2 pi to 0 to pi and confirm that the area of that circle is just pi. Do we get pi? Good.
Oh, sorry.
What happened here? You didn't multiply by a half.
I did it at the end.
Oh, okay, good. Now, take this and do it to pi, and then multiply by a half. Mode down to FUN and over to polar. Okay. Find the area of all 3 petals of 8 sine of 3 theta. Actually, let's find the area of 2 petals. You can do that. Find the area of 2 petals of 8 sine 3 theta. Go. If it helps you to get an angle down, looks like here we get to 0, then we have negative values, and then there we'd get back to 0. There's multiple ways to do it. If you find the area of all 3 petals, you can exactly multiply by 2/3. Make sure you do not double count areas. We know we have 0, 0, but when we have pi over 3, we are back to 0, right? Because the sine of 3 times pi over 3 is the sine of pi, which is 0. Which means when I go to 2 pi over 3, I'm going to be back to 0. All right, what's one way we did it? Okay, so what was your integral? Perfect. So we got to realize that we go back to 0 at pi over 3. We'll have 2 of these. Now, if we wanted just 2 petals, we could have gone from 0 to 2 pi over 3. So 1/2, 0 to 2 pi over 3. How did I figure out 2 pi over 3? Either you just are graphing it using your angles, or you're looking at when this is equal to 0. This is equal to 0 whenever we have multiples of pi. So 0, pi, 2 pi, 3 pi. So whenever we have a pi over 3, the 3's will cancel. So 0 to 2 pi over 3 of 8 sine 3 theta squared. That will give you the same thing. Or all 3 petals are actually plotted between 0 and pi. So you could have taken from 0 to pi, multiply that by 2/3. You would have gotten. Find the area of all 4 petals of 4 cosine 2 theta. Now, here's where this trips people up. If I start at 0, I go to 0, 4, right? Or 4, 0. 4 is my radius, 0 is my angle. When I get to pi over 4, I have the cosine of pi over 2 is 0. So my first location at the origin would be at the angle of pi over 4. Now, when my angle increases, everybody thinks that we're up here. So it's like we go from here, and then we go up here. Is that true? It's not true. The radius becomes negative, and this is what we graphed last class. We go down here, and we start going around this way. Now, we only get all 4 petals if we go from 0 to what angle? 2 pi. In this case, all 4 petals would be from 0 to 2 pi. Did anybody do it a different way? How did you get 1 petal? Nice. Pi over 4 to 3 pi over 4 would have gotten you this bottom petal. Okay? Is there another way you could have done it? Why not just the top half of this petal times 8? 0 to pi over 4 times 8 would have gotten you the same thing. You could have done the first pedal. What would be the angles you would use for the first pedal? Good. Negative pi over 4 to pi over 4, or 7 pi over 4 to 9 pi over 4. All different options, okay? All right, now, when we have two graphs, things get interesting. Let's look at this area in blue here, okay? We're going to do this one. I'm going to show you this one, and then you guys are going to do one, and if you do it well, we'll stop. Okay? Ms. Herbert's going to do it as well. We're going to do these problems. Okay? Here we go. This area here. Yeah. In this situation, what's important is to look at how the area is formed. Okay? Here is my radius. Here's my angle. Now, between this angle measurement and this angle measurement, right there, between here and here, and I'll just tell you that they intersect secant and cosine at pi over 3. So this is pi over 3. This would be negative pi over 3. Between negative pi over 3 and pi over 3, what is the radius? It's going to be the secant values. Okay? So almost I am going to split this up into two locations. Right here to right here, when the radius is using secant, I will have this area in red. That means right here, between pi over 3 and what value is this? So here's pi over 3. I go to what angle measurement to get back to 0 to close up the angle in blue, the area in blue? Pi over 2, right? So I have that, and then I have that. I'm going to split it up into two parts. I'll have my area in red, which will be from negative pi over 3 to pi over 3 of my secant. Right? And then I'm going to add my area in blue, which will be 2 of my areas from pi over 3 to pi over 2 of my 4 cos theta. By splitting it into two parts, it's almost like we have situations where we found, you know, two graphs, and this was one graph, and this was the other graph, and we wanted to find the area under here. We knew we needed two integrals, right? We needed to go from one point to this point where they intersect using this graph, and then we need to use this one to this one using that graph because the top changed. Here, the radius changes. So we need two integrals for that. Okay? So I would do the calculations, boom, get my area. And the reason why I do it from pi over 3 to pi over 2, I could have also done from 3 pi over 2 to, this would have been 5 pi over 3. Okay? Keep that in mind while you do a BC problem from a previous year. This one. Find the area of the shaded region R. This is R equals 3, and this is 3 minus 2 sine 2 theta. Go. Compare your answers to neighbors. Get your pencil out. Use your hand to help you figure out what radius is being used. $9.707 is your answer. Who got it? Okay, 3 of us. Let's see if anybody else can get it. 9.707. Let's see if anybody else can get it. Got it? Good. Can you do that?
Yeah.
No, you can't. What were we talking about? 9.707. Calculator's empty. Anybody else get it? We got it now? Is your calculator working here? Why secant? Why are you using secant? We're using r equals 3 and 3 minus 2 sine 2 theta. How are we doing, Miss Cameron?
Well, I tried and I got the answer wrong a lot of times.
So you just cleared it completely. I got it. You're going to have to walk me through it, Mr. Ramadian, okay?
I got it.
All right, tell me. How do you get it? All right, Mr. Ramadian, I'm going to walk you through it. When your angle is 0, and as your angle starts to increase, what is the radius that I'm using? For which function? Is it from 3, or is it from 3 minus 2 sine 2 theta?
3 minus 2.
Mr. Ramadian. Okay, good. Now, from what angle to what angle is the radius of this region R using 3 minus 2 sine 2 theta? There's 0. Yes, from 0 to pi over 2, you'd use the radius of 3 minus 2 sine 2 theta. That's your first integral, Miss Cameron. 0 to pi over 2 of this radius squared times a half. Now, what would be your second integral, Mr. Ahmadian?
From pi over 2 to pi.
Of? squared times a half. That's it. Or you realize this is a quarter of a circle, do 1/4 pi 3 squared, and you would get this answer. This is very doable for all of you. Some of you just didn't even try. There is another way to do this. Can anybody tell me another way to do this?
Yes.
No.
For part A, you
Give up
make
the
it an
next
answer so
problem.
that you can use that answer for part B.
Give us the next problem.
You can go from 0 to pi of r. You can find all of r, and you could subtract this area here. Now, how do you find that area here? Outside minus inside. So you can go from 0 to pi of this radius squared, and then subtract 1/2 from 0 to pi over 2 of 3 squared minus 3 minus 2 sine 2 theta squared. I agree. I would not have done it that way. I would have done it this way by splitting it into 2 intervals, okay? We won't do the last problem because you guys kind of stink today. So.
It's the weather. It's just